So this is a very different talk than what you are used to be hearing about, I think, because it's not extremely technical, so you might not learn too much from it, but I truly hope it's interesting. So how do you design a completely new hardware platform? And you need to start from a new chip, in this case, the NXP9310. It's basically designed to be a software-defined radio platform. It's incredible. It has 160 megasamples per second ADC, 8 DUCs, DSP, and PCI. The only issue is that you cannot buy it. So how do you design a product around something you cannot buy? And let me introduce you to the idea of access agreements. So basically, you are a hardware manufacturer, like a chip vendor, and you want to limit the number of customers that use your chips. Basically, you ask them to purchase a house from you before they even have access to the reference design. And of course, I couldn't afford it. So what do? I simply spent 6 weeks being very nice to them, and it worked. So I got access for free, and I was the first person ever to get access to this chip for free, so that was incredible. And you're beginning to think, oh, we might be up to something here. This might be actually be serious, right? So we have a chip. What do? We go to a conference, right? We go talking people to a conference. Sounds familiar? Probably the best thing I've done for that conference was sending a selfie of me outside of the conference to my field application engineer. And ever since then, we've been best friends. So, send selfies of yourself to your field application engineer. It might work out. Now, lead times. The problem and the beauty of manufacturing is lead time, right? So basically, you have to buy your chips almost a year out for a product you haven't developed yet. Just based on an idea and a concept and basically a sketch on a piece of paper. Does it work? Can you actually do it? And where do you find the money from it? So how do you raise money? Do you go to an investor and tell them, oh, I'm going to be building defendable IP on top of a 9310. Please give me money to buy the chips. Doesn't work. Bad idea. But plot twist, NXP actually wanted to build a software-defined radio. NXP knew that they had this incredible and beautiful product, and rather than, say, giving the project to an internal team that might have been, say, extremely busy, they gave it to me. So, how the flip tables, right? You go from needing to pay NXP to NXP paying you. That was incredible. The idea with this chip is that it's an IQ mixer. So, it's an IQ baseband interface. So you need to find an IQ mixer. And I got introduced to Active Semiconductors based off San Jose. And the chip on paper was absolutely perfect. We would have built the best software-defined radio ever, up to 7.2 gigahertz, etc. Of course, they knew that NXP usually charges an access fee for their chips, so they wanted a share of it. So you say no because it's too expensive. And the second option is apparently the line chip, also has an IQ interface. And this works great, out of the box, no headaches. It's great. So that was daughter board number 2. And then you start lining up the suppliers, right? So apparently the moment you tell people you're going to be building 1,000 or something, people are actually interested in talking to you. You sign NDAs with NXP, Skyworks, Granita, and you buy the chip stuff out of China. 3 people visiting your home in Italy just because you want to buy chips is weird. Crowd supply. They usually use crowd supply. I mean, that's how you do the project, right? The issue is that they take 15% and then they say, constrain you on your supply chain if you have any issues. So I decided to shoot myself in the foot and went my own way. Following step, of course, is advertisement, right? So you steal Luigi's meme, this beautiful, absolutely incredible meme, basically describing how every single software-defined radio out there is based on the 9361, and exploit it to create something new. And we managed to get to the first page of Hacker News, so that was great. 1,000 people joined the mailing list. It's promising, right? So this is what happened when the Discord server was still empty, and we only had one user on it. Basically, the user joins and wonders, why is the server so empty? I mean, is this a scam? And no, it's just, you're the first one. Welcome. User 1 has left the chat. March 2023, we're ready for manufacturing. Everything is looking good to go. Gearbells are ready to pull the trigger for a small demo batch. And then NXP wants to add something special. It is so special, it's so secure that it always delays everything. So it's a secure element chip. We only use it for the eSIM. It's inside the iPhone 15. And NXP themselves, like the people I was talking to, wanted to get me access to the chip, but it took like almost a month to do it because it's behind so much paperwork. And of course, it's usually sold by the millions. So if you want to buy 100 of them, then a poor person needs to hand program them in a lab, and it's like 10 different steps. So an absolute nightmare to work with, but we managed to do it. PCB manufacturing, if you know anything about it, the idea is you either go to China or you don't have a product pretty much. The problem with going to China, of course, is that baking to the price of manufacturing is the idea they're gonna copy the design. So if you're okay with that, go to China. If you're not okay with that, prepare your teeth for a PCB manufacturer like in Europe. I didn't want to go to China, so I tried Europe. Terrible idea. So they delivered a PCB that had a power plane short to the ground. And what do you mean you have a power plane short to the ground? How is that even possible? So you can see here there is a ground via on a power plane, and the Gerber is on the right. The actual copper is on the left. Mind-blowing. So how do you fix it? And the answer, of course, is you find a local CNC shop, and you drill it out. So yeah, good luck with that. But it worked. Got extremely lucky. It worked. And that's just a picture of the tornado head at the assembly house because, I love SMD assembly, I guess. So side effect of designing some new hardware is that you get to design the PCBs, and if you have a lot of time to design the PCBs, then people like them just because they're nice to look at. Apparently, say, golden-plated copper is actually very cool to look at. So like, for example, a NARS professor from some kind of US university retweets it, only because it's beautiful to look at. The question is, I'm sorry, does it work as well as it looks? And the answer is unfortunately no. So apparently, he was the first person to ever pair the Granita chip with the 9310, and an internal design from Actric, I think, never actually worked. So no pressure. But eventually, I brute forced the SPI address. I know it doesn't make any sense, but I brute forced the SPI address of it, and I managed to get it working. People are shocked. So recap, it's August 2023. The motherboard with hand-drilled vias is working. The Lime daughter board is working. The Granita daughter board does something, and the software is missing in action. So can I actually do the software in 2 weeks and come to GNU Radio last conference and show it? And it was the worst 2 weeks of the year, but I managed to do it. Met plenty of interesting people. People were actually excited about it, I think. And yeah, I mean, it's all looking good. So we opened pre-orders. We sell about 100 units, like 50K in sales, like 30-something% profit. You do the math, it's not sustainable, but it's fine. Shipped in 6 months. Looking good, right? So here's why I rant about the Granita issues. Number one is that the datasheet says that it goes up to 7.2 gigahertz, but it doesn't. It only does a 6.3 in practice, unfortunately. Issue number two is that to go between 5 and 6.3 gigahertz, you have to overclock your VCO, as in you don't have to provide it 0.9 volts. It has to be like 1.4 volts. And of course, that wasn't documented anywhere. Nobody told me about it. If you don't do it, only either I or Q of your phases are working. So, and you get plenty of noise. So absolutely incredible. And of course, I was promised continuous frequency coverage, which never really happened. I'm actually okay with the frequency coverage. I think it's acceptable. Like there is a slot around the GPS L1 frequency, which basically nobody uses. And you can see the progression over time for different software releases. So the dark, I have to move on, sorry. The Granita is also an harmonic generator. So 1/4 of your input clock is going to show up everywhere if you increase the low noise amplifier inside the chip high enough. So is it a PCB problem? Is it a U problem? What's going on there? And of course, a lot of finger pointing, and eventually we find out it's actually a clock generator inside the chip, and there is nothing you can do about it. Something absolutely incredible is that one of the phases of the IQ channel is off by 45 degrees. So, if most QAC cores don't really work well with a 45 degrees error, so that's another incredible problem. Not all of them, like some of the receive paths are actually okay. And of course, the low-pass filter doesn't work. As in, you set it to 20 megahertz, and the minus 3 dB bandwidth is 80 megahertz. Even though the datasheet, which is in the bottom left here, specifies, 40 plus dBs of rejection. So that's I guess that's the foreshadowing, right? So back in March 2023, they asked me to swap the polarity on some IQ pairs, and I'm like, okay, cool. And I was very excited about it back then, but I was wrong. So the ADC inside the 9310 is an interleaved ADC. What does that mean? There are 4 ADCs inside. Unfortunately, there might be some, say, I guess, DC offset, and it shows up as a FS over 4 noise. And again, nobody knows where it's coming from. Is it my board? Is it NXP's design? Is it the chip? What is it? Eventually, we managed to reproduce it on a reference design from NXP, so we finally figure out that this is a problem the IP core has. And the IP vendor doesn't have a fix. NXP doesn't have a fix. Nobody knows how to fix this, unfortunately. Eventually, the board starts shipping, and a guy named Sultan is actually very, very disappointed by this FS over 4 problem. So what does it do? He actually just fixes it. So, bother the right person, and apparently magic things can happen. I was blown away by it. We actually have a proper ADC now. This is some data about PCI speed. We can now do 620 megabytes a second from IMX to 9310. Full duplex is a work in progress. This is kind of interesting. So if you are a RFIC manufacturer and you have a broken low-pass filter, what do? You tell your customer to add a low-pass filter to the IQ lines, right? But do you think it's going to be Butterworth or whatever? And yeah, it wasn't Butterworth. So you can see the effect of phase shift over frequency on the, say, above row. And then the moment you remove that, it becomes perfect. And of course, it's very, very difficult to correct for the result on the first row if you don't have a lot of site taps in your QEC. So big problem. This is, I guess, is a different story about how you can hop on a call with a, say, big IC manufacturer, and they can promise you something, and they send you a quotation for something that's completely different. But it was all good because the 5510 was a much better device. So 5510, can you do arbitrary clocks with it? Unfortunately, no, because we haven't cracked the CRC code of it yet. We tried, but maybe eventually we will. So we just have a very long list of possible, say, DCS sampling frequencies, and you can select from any one of them. So what kind of applications can you build on top of this hardware, right? Like, can you build a 5G UE stack? And the answer is yes. So you need microsecond accuracy. People were very skeptical this was going to work, but I designed it to work, so I knew it was going to work. I was very happy about it. This is just a small fix. Another PCB manufacturing issue is when your PCB manufacturer gives you a solder mask that is way too thick. Of course, that results in extra solder deposition. And if you have LGA chips, like small switches, and you have like 70 of them in a single board, and 30% of them look like this, then it's a nightmare. It's also especially funny when your PCB manufacturer delivers PCBs with varying layers of solder max thickness in the same box. So the first batch goes through just fine, and then you reach the bottom of the box, and everything becomes absolutely terrible. And this is the rework we had to do. Basically, every single yellow or purple line spot here is a rework component. And some of those components might say kind of fail, but not really fail, so you need to test everything. It's a nightmare. So yeah, we had to calibrate every single board before shipping. Of course, you come up with a very, very convoluted testing plan, and then you just narrow it down because otherwise you're going to go insane. This is an example for the line board. This is 25 different line boards. It's all fairly close together, and I think it looks great. Again, about the UE stack. So this was a Computex. We have a fully self-contained 5G UE running inside the hardware. And I thought that was, I never thought that was going to happen. It was great. We got reviewed on RTL SDR. The only issue is that the hardware is so complicated that not even this extremely geeky person understands it, right? Like, for example, they had issues with low frequencies not coming through as they would expect us, I would want them to. But the problem is that the, say, filter bank in front of the receiver was filtering them out because the frequency was selected wrong. So evacuate is something that's too complicated, question mark. Eventually, we get a nice working daughter board. This is from Metanoia. does 2.5 to 5 gigahertz, and DVM is 3.7 on QPSK. This is just another example of how terrible manufacturing is. Like, you can trust the design from a proper, respectable SMA connector vendor, and it doesn't fit what you actually get delivered at all. So measure everything, test everything, and yeah, make sure you do that. So you have all of that. What do? You reduce the size by 95%, and you create a system on a module. And that's coming off the oven this week. And that's just a couple of pictures of assembled board, assembled heat sinks, boxes, and all of the components I had to buy a year beforehand so that I knew I could make the boards. That's it.